So we'll continue the review of probability theory. So I have just discussed how they play a part in control systems, in analyzing control systems. And I mentioned we'll put a lot of focus on the cases when W and V, they are Gaussian. So let's see what will happen if the noises are Gaussian. So Gaussian random variables and random vectors are pretty important. I have asked you just now, what is the PDF of a Gaussian? Anyone? P, let's say, I'm going to use x1. x1. What's the PDF? It's going to be, if you look at your notes, sigma x1 square root. So these are just normalization factors. The important message is it's an exponential function. It's going to be, let's say, its mean is mx1. So it's going to be x1 minus mean x1 square divided by, read my notation. So this is my notation. I'm jumping a little bit, but this is what I mean. I've told you, the PDF of Gaussian is purely described by the mean and by the standard deviation of the distribution. Only these two variables is going to determine the Gaussian probability distribution. Okay, I'm jumping a little bit. This is actually for the random vector case. So more rigorously, this should be. I really meant the standard deviation of the Gaussian variable. So now, if we have two Gaussian random variables, and I want to discuss the joint probability distribution of them, I'll first start with a simple case. Well, these two, x1 and x2, are independent. So independent means the PDF, the joint PDF is a simple product of the two PDFs. Okay? So I have expressed this equation here. Okay? My notation is slightly different, but you see it's exactly the same thing. Negative square root of 2 pi and the standard deviation. And here, negative 1 divided by 2 sigma x squared. Okay. So if these two are multiplied together, we can simplify the notation and use this random vector representation. This is going to tell us a very important message. Look at this. The first big product is simply the product of these two scalars. And then inside, this is how it's obtained. Exponential function this times this equals exponential function of the first element of this element added up with this element over here. Okay. Now just a little bit more compact representation, you can see this is exactly this guy, because if you look at the first element, this x1 minus mx1 element, so it's going to create a quadratic term of itself when we do this together. And then this inverse here is going to create this term, this element here. Okay, the same thing for this one. So this compact representation is indeed equals to this original expression. So here, this is saying this Gaussian random variable can be represented in a vector form. So if I use a vector notation, random vector notation, I can define this random vector as these two in column notation is this one. Okay, and then here, notice this one. is the, what is this one? This term here. Covariance matrix of this random vector, right? So this is the covariance matrix of the random vector. So we can express, now this is what I started at the beginning. We can express this whole thing as this compact random vector, PDF of a random vector kind of notation, okay? So here, sigma x1, sigma x2, they time together is, you can see, is the square root, right? Square root of sigma x1 square, sigma x2 square, okay? And you see here, sigma x1 square and sigma x2 square is the determinant of this covariance matrix, okay? So this is exactly this term. And this, in a compact notation, you see this immediately makes sense. This is a vector, and this is the covariance matrix inverse. So as now you see, for it's now becoming very clear that for random variable Gaussian and the random vector Gaussian, the let me say, recall the random variable PDF of a Gaussian. I want you to see that the structures are looks exactly the same, okay? Here, this 2 pi element scalar changes to this 2. This 2 means this 2 is the dimension of the random vector, dimension of x. If we have 2 elements here, it's going to be square. If we have n element here, it's going to be to the power of n, okay? And this is the standard deviation is the square root of the determinant of a covariance matrix. And then here, it also makes sense. The inverse in the scalar case is just a 1 divided by the standard deviation squared. Okay? So get familiar with these notations because they're going to be very useful. Actually, as a matter of fact, in a few more slides, I'll start using these notations very heavily. A general, so I have just discussed the case for two-dimensional Gaussian random vector. For general n-dimensional joint distributed Gaussian random vector, so I've just told you this element is going to be to the power of n. Okay, the other things are the same. Okay. So now, if we have one n-dimensional Gaussian random vector and another, let's say, m-dimensional Gaussian random vector, then we can discuss, they might be correlated, right? If in that case, we can discuss the joint probability density function. And in this sense, in this case, the structure is the same. You just have to pay attention to the scaling element here. What is the dimension? What is the overall dimension in this case? Two random vectors. It's n plus m, right? So this this scalar here is actually square root of 2 pi to the power of n plus m instead of n, instead of n. Okay. The other terms have the similar structure. And this covariance matrix is going to be, by definition, is given by this 4 by 4 matrix element. Okay. So here, let's think about it again. If x is a random vector and y is a random vector, we can talk about their cross covariance. This is telling us, think about it as the connection between x and y if they are random. Okay. So the cross covariance, if you haven't seen this before, is defined by this one. It's the expected value of x minus the mean of x times y minus the mean of y, and then transpose. Okay. So the notation is exactly, it's making sense because x is a random vector. So it's a is a skinny matrix, and Y is a skinny matrix. Take the transpose, this is going to become a white matrix. So this thing itself is a matrix. What's the dimension of this matrix? N by M, right? Because X has N element, and this guy has M element. Okay, so it's a N by M matrix. Now, because of this definition here, I can easily do this. Okay, I made some updates. If you don't have the transpose sign in your nodes, there should be a transpose sign. So I can easily do this. Okay, this guy is the transpose of this guy. Okay, I swapped the order of X and Y here, then I made another transpose just by manipulation of the matrix. Then you can see this one, this element, if I don't consider this transpose, this is the cross-covariance matrix of Y and X. Okay, so another transpose, it becomes this. So it's telling us the cross-covariance between X and Y is exactly the same as the cross-covariance of Y and X taking transpose. So in the future, if you want to verify this, always do, there's one thing that you can always do, check the dimensions of the matrix. So you have just know the dimension of this guy, sigma xy, is N by M. Okay? And this by the dimension, as you can see, is M by N. So you see, there has to be a transpose to make it equal. Okay? All right. So if these joint distributions are talked about in the sense of Gaussian, many important results can be obtained. For example, if I want to describe the probability distribution, joint probability distribution, or the conditional PDF of these variables, we can have very nice mathematical formulas. Okay? This is, I will talk about the result first, and then I will prove how each element are obtained. So this is very important facts about conditional mean and covariance when X and Y are Gaussian. So the conditional mean of X given information of Y equals, this is the equation for that, equals the mean of X. So this is the regional information of X. Now, this is the additional information. If I have information, if I have access to Y, it's going to tell us additional information of X. Same thing here. The conditional covariance matrix of X equals the covariance matrix of X minus this additional information of Y. Okay? It's going to give us additional information. So I will do the, here. I will show you how these equations are derived. And hopefully in a few more lectures, you will immediately understand why these are so important. Okay, so there are actually a hidden message over here. So it says actually this: if X and Y are Gaussian, then X given Y is also Gaussian with the conditional mean and conditional covariance. Okay? This is one of the nice properties of a Gaussian distribution. So if X and Y are Gaussian, then the conditional distribution is also Gaussian. Actually, from here, somewhere here, you can also guess that if X and Y are Gaussian, then the joint probability distribution of them is also Gaussian. So if I want to prove this one, what do you think? Where do you think I should start with? If I want to prove the first moment and the second moment of this probability distribution, where can I start with? Expected value. That's closer, very close. So think about what we have done in this lecture. I have discussed the PDF of Gaussian. Then I have discussed the PDF of a joint Gaussian. And then somewhere here, I mentioned, if I want to obtain the first and second moment of some random distributions, what is the one key element I can use? I can start here. If I know the probability distribution of these random variables, I will be able to know the mean and covariance variance. Okay? So the proof is exactly using this fact. So if I want to know, in this case, if I want to evaluate the first and second moment statistic property, then you see, everything will become immediately clear if I know the probability distribution of this. I can immediately evaluate the mean and covariance, right? So now, if I need to do this one, I can just use the joint distribution of x and y divided by the PDF of y. To make the notations a little bit more, to make everything a little bit more clear, I would use P y here, just to indicate it's a distribution of y. Okay? So now think about it. We know y is Gaussian. So that means we know this guy. We know x and is Gaussian, so we know this guy, just by several slides earlier. So we know exactly how this looks like. To be more, slightly more detailed, can someone tell me, what is the joint PDF of x and y? We can start with this easier one. What is the joint? What is the PDF of y if y is Gaussian? It's going to be 1 divided by square root of 2 pi. Then there's another, let's say, sigma square root of determinant of sigma yy, exponential function, -1 divided by 2. Then I'll have y minus mean of y transpose. Then sigma yy inverse, y minus my. Right? So I've given you this one. Someone tell me, what is this one? So now in this case, so let me use this notation. The sigma here is defined as sigma xx. So this is nothing but the covariance matrix of xy. Okay. So let's see. Let me update a little bit. I would like to consider the case where x and y are both vectors. So let's say x is n-dimensional. Let's say x is n-dimensional and y is m-dimensional. So just for the general case. So here we're going to have x minus m of x, y minus m of y, sigma inverse x minus mx, y minus my. So this is immediately using, this is why I told you these PDFs are very important. The form of the PDF are very important. So this is using the PDF of a Gaussian random vector. There are basically 2 terms remaining to be done to be able to do this proof. Okay? If you look at this one, I will have to know determinant of sigma. And I will have to know the inverse of sigma. These are the only 2 terms that's blocking me from obtaining a nice formula over here. All right? So I would like to now start with discussing the two elements. So if sigma is sigma xx, sigma xy, sigma yx, sigma yy, this result is important, is useful regardless of whether we're doing control engineering. It's used also in statistics and many other fields in linear algebra. If I give you a matrix and I want to evaluate the inverse of it, there are several ways, and this is one way to do. So I can somehow, this is the basic idea. Let's say, I can somehow do a similarity transformation to make it diagonal. Okay? I can somehow do a similarity transformation to make it diagonal. And these T matrices are simple enough such that the inverse is easy to compute. Then in this case, I'm going to have sigma inverse. I'm going to take the inverse of the entire element here equals the inverse of this one. Then I will be able to evaluate the inverse matrix here using this result. So let's see, what is one way to obtain this similarity transformation? Okay? If you remember, if you can do the case for two-dimensional matrices, you'll be able to do this. So imagine what will be sigma xx, sigma xy, sigma yx, sigma yy. What will be some matrices that's going to give me this? Let's say I want to do this step first. This is one element that remains to be obtained. What is one matrix multiplied on the right, meaning operating the columns of this matrix? That's going to give me, that's going to make this element, this bottom left element, to be 0, and this second column to be exactly the same as the original one. So I have 4 things, 4 elements to determine. 2 of them are very easy. The remaining 2 are a little bit difficult. X inverse, you mean this inverse? Inverse of this? Sigma yx inverse. Sigma. Yeah, they're not square, so be careful. So the first, the 2 elements here are relatively easier. So the column here and the column here are the same. I'm not manipulating the second column at all. So this element here, these 2 elements here has to be 0 and 1. I'm not manipulating the second column. So this has to be 0 and 1. Now this one remaining, this, let's see, we probably can start, we can do this both by derive the additional 2 elements by looking at this one. So I want to be able to sigma yx. So I want to be able to express, I want to be able to make this one to be 0 after some combinations of the second column here, right? You mean, recall that matrix multiplication on the right just means column operation of the matrix, okay? So somehow, I got to be able to massage the 2 column, the elements of these 2 columns to make this 0. So this is one way you can see. Yeah, this is the way. Okay? So is this element minus this guy times this element? Right? So put it in the matrix. This means nothing but I'm not manipulating the first column So this is identity. And then for the second column, I'm putting a matrix here, negative sigma yx sigma y inverse. So it looks like this one works, right? So let's check it. So the column here is the first column of the matrix minus this guy times the second column here. And this element here is exactly, so the first column minus this guy minus this times this, right? This is 0. Everyone with me? Huh? Oh, yeah. I should do the other way, right? I should be doing sigma y sigma, yeah, you're definitely correct. I do this, right? So things will work. So it's gonna be these two guys, the orders has to be switched. Let me make a correction. Negative sigma y inverse sigma yx. Yeah, it's multiplication on the right. Okay? So if you don't get it, I'll do one more. Then you will be able to know immediately. So now if we are given this, what is the element here? Let's check. It's going to be the first element, sigma xx, then minus sigma xy times sigma yy inverse sigma yx. Okay? So now we're one step closer to making this completely diagonal. Okay? Now let me copy down this matrix here. Let me copy down this one. Now we have, this is step 1. For step 2, now we have this matrix zero, what will be some matrix operation on the left, and it's going to give me diagonal, completely diagonal matrix. 0, 0, sigma yy, sigma xx, minus sigma xy, sigma yy inverse sigma yx. Okay? So let's do it as an exercise. What will be some matrix operation on the left that's going to give me this one? Again, I think two elements here are relatively easy to obtain. I think the first column, no, the first row, either the first column or the first row are relatively easier to obtain. All right? So someone can take a guess. What will be some of the elements here? 0. Which one is 0? Second, this second row. This one is 0, right? So this is because the second row of this matrix remains unchanged. So that means the operation on the left, so matrix multiplication on the left means row operations. So that means I'm not changing the second row. So this is exactly what it means. And you can check 0i times this element is going to give me 0. 0i times this guy here is going to be this one. Okay? So the remaining two elements are slightly trickier to obtain. But the idea is the same. Okay? So let's do it together. First of all, I see that this element is the same as this element. So the matrix here is identity. I'm not manipulating this guy here. And this remaining element, let's say, okay, I have to be able to do this step. I have to be able to identity times this guy, yes. So if I look at this operated on this guy, so I'm aiming at this element here, 1, 2 element here. So by matrix operation, mathematically, I am getting I have to use this operation to get me 0, right? So this way, I'm going to obtain this element here has to be negative sigma xy, sigma yy inverse. I first shift this guy to the right, and then I times both sides on this guy's inverse. Okay? So as a summary, this is what we have achieved. We have done, this is the matrix element here. We have used the left matrix multiplication and the matrix operation on the right to the original matrix to create a diagonal matrix where the diagonal elements looks like this one. Okay? Now, it becomes immediately obvious. This is immediate. What will be the determinant of this matrix? So I take the determinant of both left-hand side and right-hand side. The determinant of this guy is 1. The determinant of this guy is 1. So the left-hand side is exactly the determinant of this whole matrix, the covariance matrix. And on the right-hand side, the determinant is very easy to evaluate. So it's a determinant, it's the product of the determinants of these guys. So, okay? So this is very easy to obtain this determinant, which will be useful for the PDF, in the PDF expression. Okay? And by looking at this one, we mentioned we also need the inverse. So we also need the inverse of this matrix. You can see that this is also very convenient to obtain because the inverse of this guy is easy. The inverse of this guy is also easy, and this guy is also easy. So we can take the inverse for these for this equation here, equation 3, and we will be able to get here the result here. So the inverse of this guy is nothing but the inverses of these two guys, and then the inverse of this guy. The 3 of them combined together. Okay. So this this is straight linear algebra, so there's not many tricks here. Okay? And we will be able to get this one. So let's recall what we wanted at the beginning. We wanted at the beginning to be able to evaluate the conditional joint distribution of x and y together. So recall we wanted to do this one. We wanted to be able to express this combined term here. Okay? So now we have easy access to the inverse matrix, and we have easy access to the determinant. Okay? The remaining part is this guy. So we have to express this expression for the p, x, and y. All right? Yes? are inverse of each other. It turns out by the construction it is exactly. So if you, let's see, the T matrix, let me find it. Where's the T matrix? Here, let's denote this as T. Okay, then if it's a similarity transformation, this guy has to be the inverse of T. Take a look, see whether it is. This times this. Let me check my notations. I take back what I said. It doesn't have to be a similarity transformation. The only requirements here are determinant is 1 to make this happen. That doesn't have to be a similarity transformation. Everyone sees this? So it doesn't have to be a similarity transformation to make this happen. The only thing required is determinant is 1. All right? Mm-hmm. Yeah, the basic idea is doing these operations to make this diagonal. And the process, if you think about it, is actually similar to the case for 2 by 2 matrix in the scalar case. Because I want to be able to get this one very easily. Mm-hmm. Why? Mm-hmm. T sigma. I did sigma t, but it's similar. Yeah. Mm. Yeah. Yeah, but in this case, so it turns out it's not exactly the inverse of t. So I took out this statement. It doesn't have to be a similarity transformation. Yeah. The main reason, actually, we could have stopped at the first step if I want to just obtain determinant of sigma. Because at the first step, I already obtained the diagonal, upper triangular matrix. So I would be able to express the determinant in the first step. I did the second step because I wanted to do here. I did the second step because I wanted to do this guy. I wanted to be able to easily express this term. And it's nice if this guy has sort of not exact, sort of symmetric properties inside. So I would have something that's going to be able to be combined with my term here. And I would like to have something that is going to be combined with the term here. So that's why I did the second step. And immediately, if we use this guy multiplied by this guy, I'm going to get exactly. I'm not going to change the second row of this. So the second row remains the same. And in the first row, it's going to be I times this guy, which is x minus m of x, minus this times this. So you see exactly this times this. Okay? This one, if you see it, if you see the mathematic expression of this guy, what do you recognize it as? It appeared several slides earlier. I used this notation. The conditional mean of x given y. Right? I told you this is the original mean of x, and then this is the additional information that's given, offered by y if we do this. Okay? So, okay? So finally, it's going to be very easy to express this term here. Bring back the slides. It will be very easy to obtain this operation here, because now you see, for example here, now you see the determinant of sigma. If you check the note, it equals determinant of sigma yy times the determinant of sigma xx minus sigma xy, sigma yy inverse sigma yx. Okay? Because of this, you see, this guy is going to be completely cancelled, right? Here. This element here is going to cancel this element here. Okay? So, and on this side, I'm going to have, if you remember, if you take a look at the expression of the sigma inverse, you will see that here it's amazingly easy to express this term, because, look at this term, because the inverse is now diagonal, right? Because the matrix is now diagonal. So it's very easy to express this term. It's going to be just, let me write it this way. It's going to be x minus mxy transpose times the inverse of this guy. Sigma xx minus sigma xy, sigma yy inverse, sigma yx inverse times x minus mxy plus y minus my transpose, there's a transpose here, times sigma yy inverse y minus my. Okay, so now if you, this is times, this is plus, yes, correct. Now, look at here. If we use this information, if we use this expression here, what will be the expected value of the summation of two terms? It's going to be the product of the expected value of each element here. You see here, one element is going to cancel this term. The term that's coming from here is going to cancel this term. So you see, the remaining part is just going to be the expected value of something that contains this term here. Okay? So everything becomes very clear, and this is the result. So it's going to be here. This is the expected value of x given y, and this is the big covariance matrix inside. And if you check the notations I used earlier, this is exactly sigma x given y. Okay, so now look at this expression, this result carefully. The conditional distribution, the conditional PDF of x given y equals to this some scalar term times some exponential term, exponential function of this. So it is exactly, you see, this is exactly in a form of Gaussian distribution PDF, right? With the mean here, and with the covariance matrix here. Okay, so any questions for this part? So this is concluding that, giving us the conclusion that x given y is a Gaussian, first of all, and then mean, covariance, all of them are given to us now. This one, we can use capital Y here as well. Here, the more important is this notation here. So here is the mean of a random variable, so it has to be capital X. And then given some measurement, some value of Y, so it has to be small y, right? Here, the small y doesn't appear actually for the covariance matrix, so yeah, it's your choice. So yeah, as you are speaking about that, in this class, there are actually not standard expressions for covariance matrices for this notation. Sometimes the covariance matrix, let's say, sigma xy, will be written as xy. So the reason for that to make sense is covariance matrix is expressing some kind of correlation between x and y. Okay, so x means cross, so it means some sort of correlations between x and y. So this one will also be used in the class. Okay. So now, think about it. We have done, for the first half of the class, for the first half of this class, the discussion of probability distribution functions of two random vectors and how the result is going to look like when they are Gaussian. We can do a very long vector of random variables. Okay, so in this notation, it's x1 and x2. Each of the element here, x1 and x2, is a random variable. We can stack these random variables in a long vector. Okay, and then this is important in the sense, for example, in a system where you have a long vector of measurement y0 to yk, like this one. Okay, so it's useful to discuss, if we have this case happening, how the statistic properties of this is now called a random process. So at each time, the random variable is a random variable, but we have a long sequence of the random variable, so it's a process. Okay. In a picture, it looks like this. For example, if I do one experiment today, let's say I measure the temperature of today. So I can have, at different time of today, I can have measurements. So suppose it looks like this. Okay, it's going to have some fluctuations. So if I do the experiment today, I can do the experiment tomorrow. And tomorrow, at the exact time, the values of the temperature is not going to be the same. There's going to be a difference. But it's, again, there's some randomness inside. Now, if I do this the day after tomorrow and then continue doing that, each day I get a different randomness inside. But let's say this is 1 o'clock, 2 o'clock, 3 o'clock. But at each time instance, 1 o'clock, 2 o'clock, the values of x has certain kind of distributions, right? So at each time instance here in this example, this is a random variable. Okay, so it's going to have, for example, let's say it's summertime and the average temperature there's a fixed average temperature, but each time when we measure it at one time, temperature is going to have certain fluctuations. So that's the randomness. That's the random variable. The temperature at 1 o'clock on each time is a random variable. Okay? So that's a construction how we understand the random process. If you think about it, to be able to express, to be able to completely understand how this random process looks like, we have to know the complete probability properties defined by the joint PDF. Each one of them is a random variable. So the complete information is defined by this joint PDF. But as you can guess, it's very difficult to obtain usually. So we will be using, for the majority of time, the mean and this is a new notation, autocovariance. But it's very related to what we discussed before. So the mean is there's nothing special about it. So it's just the mean of this random variable at time k. The autocovariance is defined by this. So it's discussing how the random variable at time j is related to the random variable at time k. So it's just a definition over here. So each element here is a scalar. So that's why I don't need a transpose here. Okay? So the notation here means the autocovariance of x, so of x, with the time indexes j and k. So it's discussing how a process at different times are related with each other. So I have talked about this. Sometimes the sigma notation is replaced with x notation, big X notation. So things get a little bit more interesting for the case of random process, because think about it. If I'm measuring the temperature every day, I can do a time average for today. I can also do a time average of the 1 o'clock temperature, let's say, over a month period, right? So I can have two sets of averages. So the time average of x of k is defined by xk upper bar, which is exactly as you can imagine. It's the average value of x at different times summed up together. Okay? This is slightly different from what we have been using, which is now called an ensemble average, which is really the mean value of x, what we have been using before. So it becomes very important if we have two notations together. It will complicate certain things, and it will make the situation much more difficult to analyze. So what we discuss usually in this class is something called ergodic random process. So it simply means one condition it has to satisfy is these two mean values, these two averages has to be equal to each other. Okay? So more more advanced properties is that not only the first moment has to equal to each other, but also the second moment, the covariance, in this case is autocovariance. The autocovariance of the x of k, the random process, has to be also equal to the time average of the random process defined by this one. So as I mentioned, this is going to bring us a lot of simplifications in computation. Okay? So in practice, as you can imagine, because this is time average, this n is infinity, as you can imagine, it's very difficult to evaluate all these moments, this time average of the moments. It's very expensive to do that. So it's not very easy to test whether a random process is ergodic or not. But many processes in practice are ergodic. there is sort of difference here. Now, if you look at the notation carefully, when I say expected value of xk, this means of this random variable. It means the random variable at time k, right? So in the example of measuring the temperature, it would mean at every day, 1 o'clock, this random variable, I take the average, the mean of that. So that will require me to do average of every measurement at 1 o'clock, right? But this guy is slightly different. This is average over this index j. So that means for today, right? If today I can take a lot of measurements, right? Mm. So that will require me to do the average of all these values. Yeah. But this one, the notation, the definition here is different, right? This is 1 o'clock, temperature, 1 o'clock, right? This one? Yeah. So this is the covariance, autocovariance, which I defined earlier here. Is again, the difference is again that, yeah. Okay? So we're talking about ergodic. It's difficult to evaluate because it requires not just mean autocovariance, but we haven't talked about, but there are third moments, fourth moments of statistic properties. But ergodic random process to satisfy all these moments has to be equal to the time average. So not easy to verify, but important in practice. And in many practical cases, this is true, that random processes are ergodic. So you can immediately see the complication when the process is not ergodic, right? So in control engineering, we want it to be ergodic. If it doesn't, we create it. We set up our hardware to make that happen. The reason for that, think about it, is, for example, I want to do control a system. I don't want it to be different if I start the experiment in the morning and I start the experiment in the afternoon, and it's completely different randomness inside. That's going to be tough for any kind of control, right? So we want it to happen. A very necessary assumption for process to be ergodic is called stationary. As the name suggests, stationary tells us whether the statistic characteristic change with respect to time. So it's in everyday language means, for example, if I'm doing experiment, I don't want to have a difference doing it on Monday, on Tuesday, on Wednesday, or doing it at different times of the day. Okay? So in a strict sense, stationary means the probability of the random the random variables. There's not going to be a difference if I consider this at time k1 to kn. And then the case if I just shift every time index by a number, L in this case. Okay? So I don't want this one to be different from this one. That's the stationary in the strict sense. So do you think this one is easy or difficult to evaluate? This requires the full probability properties of the random process. So it's sort of still very difficult to evaluate. In practice, we often check whether a process is stationary. This is called weak or wide sense stationary. So it means the first moment and the second moment are sort of time invariant. Okay, so it's again from going this complicated result to a simpler to check conditions here. Any questions? Okay? So if you don't have questions, let me ask you one. What will be what will be, let's say, expected value of, what will be the autocovariance of XX J K plus L? What would be the definition of this guy? You can check your notes. So it's going to be, this is one example to check, because I have a feeling that some of you are lost. So the autocovariance of this guy is the expected value of x at time j minus the mean of x at time j times x at time k plus l minus the mean of x at time k plus l. Right? The definition of autocovariance. Now, if you immediately see why this is at least something we have to, some properties we have to know for making everything work. So if this process is stationary in the wide sense or in the weak sense, then the expected value is a constant. So I can immediately reduce the complexity here because these guys are equal to each other. It equals to mean of x. Okay? Now, what does it mean for, let me ask you, what does this statement mean? The autocovariance depends only on the time difference. So it would mean expected value. So this is the autocovariance XX, let's say, I'm going to use the notation Kj. Okay? So it means the autocovariance for the time indices K and J, which is defined by this. Now I can safely use mean of x because I'm saying here the mean of x is constant for the stationary in the weak sense. J. Okay? So this statement here simply means if I do this autocovariance this case, then there shouldn't be a difference if I do it at this time. So look at this. All right? It's simply saying this. If I'm going to evaluate the correlation, sort of the idea of how xk and xj are connected, then it doesn't make a difference if I'm going to do this all shifted by, let's say, 1 day. Then this should be exactly the same, these two. Is stationary. So it simply means, again, that the statistic properties doesn't change with respect to time for these properties. All right? Here it means the mean doesn't change with respect to time. And here it means if I'm checking whether these two, how these two are related, then I can do this morning. I can also do this afternoon, as long as the time index is the same here, j minus k. All right. As long as the difference of time is the same, then the autocovariance is the same. So first of all, we started ergodic processes are important, but it's very difficult to check. And then we ended up saying that one necessary condition for ergodic is stationary. So now that's why we are evaluating stationary case. And then over there, we started talking about in the strict sense, which is difficult because it requires, you can see, the full probability distributions of all these. Then we say, this is very tough, still tough, but the weak case we can very easily verify. Okay? So this is what I have just written down. So because of that, you see here, because this autocovariance depends only on the time difference, J minus K. So I can make the notations a little bit more simpler. So I can write down this. This is the, if I'm using the previous notations, this would be XX, the first index is K, the second index is K plus L. So this would be my original notation for this. So first index K, second index K plus L. Now, because we know now the time for stationary case, it only depends on the time difference, which is L here. So we can write it this way. Okay? So the difference, the time difference between these two elements. And sometimes we will also, again, going back to the idea, the intuition we talked about, we can replace sigma with X to say autocovariance. Okay? For a stationary and ergodic random process, now this we just have derived from here. Because it's ergodic, so that means if I want to evaluate the mean, I can do the time average. Okay? So this is the properties of ergodic random processes. Okay, so think about what we have done here. We have been talking about sigma x of x. It's autocovariance. It's something about x itself. Imagine we have two random processes. For example, here, I have both x and y. They both have time indexes. Then we can do this. We can think about how x and y, these two random processes, are related to each other. So it's meaningful to define cross covariance. Cross means it's between something, it's between two things, x and y here. Okay? So the definition here, cross covariance, is this guy. It's how x of k is related to y k plus l when their means are taken out. This is the definition. So as you can recall, the definition of sigma x of x is simply replace this y with x. Okay? So here, I have already started using the usual assumption in our course that we're usually going to assume processes are stationary and ergodic, unless we explicitly say it's not. They are not. These assumptions are not whole. Okay? There's a definition of autocorrelation, which is defined by Rxx. So this is related to the autocovariance in the sense that in autocovariance we have removed the mean, and in this autocorrelation the mean wasn't removed. Okay. This definition has the definition of autocorrelation is not standard between control engineering and digital signal processing. And in statistics, in control engineering and in digital signal processing, this is the usual definition. So the mean wasn't removed. In statistics, there are definitions that this guy is exactly the same as this guy. But we'll be using this usual definition in control engineering. Okay. There is one last property I want to show you to end up today's lecture. It's this one. So I want to show you the equal signs here. The cross covariance of x and y is the same as the cross covariance of y x. Look at the notation difference here. X, y, y, x, but the time index is shifted. It's the negative of this time index here. So the proof is actually very easy. So it's just use the properties of ergodicity. So using my notations earlier, the cross covariance of x and y simply equals to, by definition, expected value of xk minus m of x, yk plus l minus my. All right? So now, if the process is ergodic, then this mean is the same as we can compute the mean from the time average. So I can use this notation here. And then I can easily swap the orders of these two. And this equals to, if the processes are ergodic, this equals to the expected value of yk plus l minus my, it should be used capital Y's, sorry, xk minus mx, which is equal to the, you see here is the only thing that you have to pay attention. So this guy, by definition, equals to the cross covariance of yx, because y comes first. And then the time index here should be the time index of here minus the time index here, k plus l. So it's equals to negative l. So here, this is the final useful result for today's lecture. Okay, so by now, probably you will be able to solve most of the problems in homework number 1. Okay, in the next lecture, we'll talk about how, if we are filtering. Now, I haven't talked about transfer functions or anything like that. Now, next time, I'll talk about if you have x and y, I filter this through a transfer function, what will happen? Okay, see you on Thursday.